Yes.
632.
Yes, I think so.
All right. Okay. Huh? Just in time. That's my name. So, Ahmed. Yes. I'm Justin. This is Ahmed. In case you don't know, we are the co-hosts of the user group called Just Enough Mad. And what is our goal, Ahmed?
Our goal is to present just enough math. See what I did there? So basically people who are involved in any aspect of software development, even if it's like testing, PM, could find tools that can help them in the job without having to go, deep in the weeds. So like we're not gonna ask you to prove anything or anything like that, but show you like packages and concepts that can basically make your life easier. And again, a lot of stuff is stuff you can just do by just calling a package. And we just give you a kind of the high level conceptual understanding. It goes a little bit more into the weeds for those who are interested, but that's the idea behind it.
Yeah, and I think today might be a little bit of a weeds kind of day.
It's a weeds day.
That's why I don't go.
So this might be like just a little more match than you need.
Yeah, notice how I'm sitting down, so you can tell there's going to be a little bit of a deeper dive.
Yeah, so I sort of took this one over because this is a topic I really like, and I feel like the math is really accessible. And I mean, so the general topic is going to be neural networks, right? We're going to show basically what a neural network is doing, or at least part of what it's doing when it makes a decision about something, right? So there's math, the math behind this. I claim is fairly accessible. It's mostly high school level math. There are going to be a lot of matrices involved. The core concepts are going to be functions and matrices. So, all right. Should we do our usual disclaimer? We don't claim to be experts, right?
You don't claim to be an expert. You're doing this on your own, right? So you're not the expert. You're claiming not to be an expert.
Right. You're not taking any of the credit or the blame.
I disclaim nothing.
So I don't claim to be
We
an
don't claim to be
expert,
experts, but we are.
but we know what we're talking about. And also, the opinions expressed here do not reflect those of my employer.
Yeah. Controversial opinions on neural networks.
Yeah, we could have some controversy in there, some math controversy.
Yeah, not to polarize like with your algebra. So.
Yeah.
And no animals were harmed in the creation of this.
That's true, also, although maybe not true. That may not be true. There were a lot of rare earth minerals went into this machine, and I'm sure some animals were harmed by that.
Hey, can I ask you,
Yes.
what is your day job, since you brought up your company?
Lodestar. I teach math at Lodestar.
Okay, cool.
Yeah. Thanks. Yes. Ahmed is, although he takes none of the credit or the blame, he is a co-host normally, and he's here at Improvement, right? Software developer.
Yeah, software developer here. So.
Yep. So we decided to team up because we have different perspectives on these things, and we basically argue a lot, and we just wanted to share that with you.
Very small.
So what I'm anticipating is that Ahmed is going to be like super like peanut gallery right today. In fact, yes, Ahmed, you have like carte blanche. Just stop me to clarify anything that needs clarification.
Okay.
Especially like from a software development point of view, because like I don't really have that point of view much. I mean, I know a bit, but I need help to understand that point of view. So yeah, chime in, please. Anybody chime in?
Yeah, if you did this collaborative, if you have questions, please don't hesitate to ask. If you have like different experiences, you've done some of this, please share. I mean, we definitely want this to be more open, not just like, hey, this is a lecture. Okay?
Yeah.
Can we heckle?
Can you heckle?
Yeah, heckle.
Heckle away.
Heckle. You'll see how I treat hecklers.
Oh, God. Oh, you know what? He scares me sometimes. Yeah. I mean,
Ahmed is my chief heckler. It's like, that's his official
I was
title.
asking for all.
All right, so the preliminaries are here, in the.
So real quick,
Oh, yeah.
like, can you give like a sort of like just a quick sort of TLDR into what you're going to talk about in this session? Like too long didn't read, just a quick summary. Like linear algebra, neural networks, just kind of quick overview so people kind of know what they're in for, if you don't mind.
Good idea. So a neural network is a machine learning model. Early applications even included like self-driving cars in very controlled conditions. It's a parametric model, so it has a bunch of these parameters that you try to estimate using data. Like you collect a bunch of data, it's a statistical approach, right? So you collect a bunch of data and you try to estimate the model parameters using that data. The context that we'll be speaking, or that we'll be in for the duration of this presentation is a neural network designed to perform a classification task. So meaning, it's going to decide, it's going to look at a specific data point and decide whether that data point represents a certain type of thing, right? So I have a more specific explanation to talk into that in a minute, but that's the idea. So, a neural network must be trained using data, right? So it basically kind of works. The idea is like it works the way our brains work, which is that you give it enough examples of a concept, it figures out that concept. Right, like it sees enough examples and then it tries to learn the overall concept. Like, another classic example might be like identify, the dog in the picture or something. Like, is this a picture of a dog or is this something else? Right, like so classification, dog, not dog. Right, so it would take that visual data, process it in some way. Pictures of dogs will have certain attributes that it can pick up on. Right, and all this is done with math. Like, it's all entirely done with math. So what we're going to talk about today, basically, is we're not going to go into, well, I'll tell you what we're not going to talk about. We're not going to talk about the training process. We're not going to talk about how the neural network learns. We're just going to talk about what the neural network does to classify things once it's learned to tell the difference between dog or not dog in the network, right? So it's just a calculation. Is what it does. It just does a fairly elaborate calculation, and it comes out with something, and it says it makes its decision, right? And so we're just going to learn the math behind that, and we're going to visualize what's going on inside the neural network, so to speak. So it's a sort of, at this point, almost cliche to say that machine learning models are black boxes, right? We don't know what's going on inside the black box. This is true, but we're still going to look at what's going on. We're going to look inside the black box. The caveat to that is,
There's going to be plenty of graphs, so you're going to just get visuals. It's like,
yes.
it's a whole bunch of theories.
At the very end, I'm gonna sort of pop the hood, so to speak, and see what's going on inside the black box. Now, the caveat to this is that I may not be able to explain why or why this is going on inside the black box, but I can show you what is going on inside the black box, right? And maybe we can think of some reasons why, or how, like why is the neural network operating in this way? So that's a good topic for discussion, I think.
The other thing also, just a very quick intro, like what is linear algebra? What does this have to do with anything? Just kind of a quick, just again. Overview.
Yeah. Well, okay. So, linear algebra is the study of matrices. That's all. Do you know what a matrix is? So, if you're in software development, you know what an array is. And, a matrix is a 2D array. Right. So
A table of numbers.
yeah. It's just like, it's an array of numbers, you know, it has rows and columns. And that may seem like a silly little construction, but it's actually extremely powerful. So, I mean, linear algebra is a super deep field, and we're not going to go into it. We're just going to study matrices a little bit, you know, and learn how matrices play a role in the calculations. Yeah, we're not going to do any of the deep theorems of linear algebra and stuff like that.
Yeah, that works.
Yeah.
So is this sort of synonymous with like data structures or?
Yeah, matrix is a data structure, right?
Yeah, it's a type of data structure. Yeah, so fun. And the thing was a type of data structure where you have certain types of operations defined on it. Like there's certain like, you know, multiplication, like it's defined in a special way on matrices, but it absolutely is a type of data structure.
Yeah, because I've always wondered like people really were the linear algebra programming, so I guess.
Yeah, searching.
Yeah, I mean, the primary thing is like, yeah, like a matrix is a data structure. That's just the first point of contact, I would say. I mean, well, the more abstract theorems of linear algebra probably don't have applications immediately. I mean, like, I mean, not immediately. There's probably some connection, but I'm not really an expert on that.
Maybe radical.
Yeah, like or like special applications and stuff like that. You know, so. I mean, there are a lot. You can bring up a lot of concepts like, you know, like a basis for a vector space. I don't know if you're very taking linear algebra, but like, you know, some of these concepts that you learn in like a senior level or graduate level linear algebra class that I don't know that they have direct applicability to computer science. But
It's really just like bare bones linear algebra. So basically just like a bare bones. Like,
Yeah, it's the bare-
one
it's-
and linear algebra.
yeah, it's really, we're going to talk about matrices, basically. Yeah, but not like the deep properties of matrices, just kind of what they are computationally. That's all. Okay. So, any other questions? Where did Ahmed go? It got quiet.
I feel less nervous.
So in the preliminary section, we just, you know, there's a lot of stuff we're just going to skip over, but you can find all, you know, the functions that I make use of down below. So stuff that's relevant immediately to the conversation will be like activation functions. That's a part of neural networks. Okay, so we will talk about those. And then, you know, then here in the neural networks functions section, you know, this is where we actually use the package called sklearn from Python. It's a machine learning package in Python. So
Yeah, for those of you who are interested in doing any machine learning and haven't, yeah, Python has a variety of packages. sklearn is one of them. There's also PyTorch, TensorFlow. So there's quite a few. That's why a lot of people like to do machine learning in Python. You've got them in other languages too, but Python makes it easy. There's a whole bunch.
yeah. So if we were to feature a package, that would be it, right?
And-
sklearn.
Yeah, and just so everybody knows, I did post this link in the LinkedIn group, so you can access the same sheet that Justin's using. You can save a copy, make your own changes, play around with it. All the code's executable. So you can do it at home, you do it now. If you need the link, you can't get a hold of it. You're not on LinkedIn, let me know. I'll make sure you can get it.
Yeah.
There's nothing to install. You can do this all in your browser.
Yeah, and that goes for all of our talks
Yeah.
in the future and the past.
If anyone wants, I give you the full list of all of our talks.
Can I send you a link for one in the future?
I could probably do that. 'Cause it's probably gonna be SimPy, but that's a whole other thing.
Fine.
Right,
Careful.
yeah, we can try. We'll work on that.
Is there the group that this is all related to? I mean, a lot of times we bounce things to a Discord group, so what's the core group that this whole class is related to?
This is a LinkedIn group called Just Enough Math. There is a Discord group that has one lonely member, which is me. You're welcome to join a Discord group.
It doesn't sound that exciting.
What's that, just supporting the justice?
Just one guy. One join.
I'll say doing it because I could really use some company because it's sad and lonely in there, and I'm feeling pathetic.
Hey guys,
What
what do you
do
think
you
about this? And he's only.
Yeah.
I just learned that LinkedIn has groups.
Yeah, so did I when I actually found this group. That's when I first found out. But I can also send you directly the link. So if anyone want some links directly, let me know, I'll email them to you, I can get you all of our past links.
I can dust off my credentials and when I get to Lakeland.
Okay, but just holler, if you have any trouble getting any of this stuff, just let me know. I'll make sure you get it.
Maybe you could drop the QR code into the sheet.
Yeah, I'm gonna do, yeah, oh, you did it with the QR code?
No, I don't really even know what a QR code is.
I'll get the QR code, at the end, I'll put a QR code for the LinkedIn group, and also for the survey, just to see how we did in the class, or how we did.
Yeah.
So
Exactly.
Force them to join the Discord.
I'll put them all on Discord too, I mean, I've got the whole list of all the
So
links.
why would you put yourself on all that work? If they really want it, join the Discord.
Damn, I'm a people pleaser.
All right.
Okay,
So
so,
that was quite candid comment. Thank you. All right. So this is the starting with the meat of the topic here. So like I said, I claim that you can understand basically the calculation of neural network does just with high school math. Okay. So we're going to start with high school functions. All right. If you remember, go back to high school, you learned about functions, and you had an input variable and an output variable, right? Your input variable, for whatever historical reasons, we call it X. The output variable, we often call it Y. We give functions names like F. Okay. So in software development, this is not an alien concept, right? Like you give names to functions, they take certain inputs, produce certain outputs, right? In high school, basically, we were thinking about mathematical functions. The inputs and outputs are numerical, right? So one numerical input, one numerical output, right? All right. So, we write y equals f of x for the equation of the graph. We think about the domain and range of the functions, and I'll have a visualization below to talk about those things. But basically, the domain is your set of possible inputs, right? And the range is the possible outputs that could be produced by putting those inputs in, right? All right. So,
oh, real quick,
yeah.
Nowadays, they also sometimes call the range the codomain, right?
That's old terminology.
That's old terminology.
Yeah, I mean, sure.
You'll see it sometimes. Sometimes you take a look at, let's say,
Yeah.
domain, codomain.
The
That's
domain
its
and
range.
codomain, it's, these are textbook terms.
Yeah, but for programmers out there, think of the domain as the type of the arguments, and think of the range as the type of the function.
Yeah.
That's pretty. Huh?
Okay. All right. So here's our little visualization of domain and range. Here. Just take a look here.
Want to make it smaller?
Yeah, I kind of zoomed in.
Yeah.
Because my font is two different sizes. That's all. So here's the visualization, right? So the domain and range of this, so first of all, this is not just one function. Functions don't move. But if I pause this, that's a function. That's the graph of a function, right? And the domain is around here. The domain is this green bit, okay? So so the horizontal axis is the x-axis, the vertical axis is the y-axis. So for this particular graph, right, these numbers that are on the x-axis down here are the permissible inputs, right? Those can all be inputs to the function, and then the outputs live here on this red line segment on the y-axis, right? And an input-output pair, right? Those numbers are points on the graph. That make sense? So say this is an input, right? Then the corresponding output is here, and the coordinates on the graph are a pair of numbers, an input and an output, right? Okay.
That makes sense, everybody?
So the real takeaway here that's relevant to what we're doing is that the domain and range can be visualized separately, right? The domain and range are different from the graph. They're connected to the graph, but they're separate entities, right? In this high school function case, the domain is a certain segment of the x-axis, and the range is a certain segment of the y-axis. So the inputs live in one place, and the outputs live in another place. The graph of the function actually, for the rest of for our talk today, is not going to actually be super relevant. The main point, again, is that the kind of the domain and range can be visualized as their own separate entity. As you can see, you know, of course, the function determines the kind of the shape of the range, right? So if I change the function by sort of like scrolling this b parameter to, so this is a different function. So now you see my range and domain are different now, right? So they both depend on the function, right? All right, so let me see, make sure I didn't miss anything in these bullet points here. So yeah, the graph represents a relationship between x and y, and the graph is just a visualization of the function itself, right? So functions are meant to represent relationships between two variables, x and y, and the graph is just a way that you can visualize that, right? So the graph is more or less, in the high school context, the graph is more or less the full picture of what's going on. You can see the relationship, right? If I look at this, I can say, well, for this particular function, what can I say about the relationship between x and y? Well, okay, if x is here, right, and I start moving that way, then because this graph looks like it's sloping upward from from left to right, then I can say, well, y is increasing as x increases. And, I see a full, if you read it right, it's a full, visualization of the relationship between x and y. The graph itself lives in two-dimensional space, right? But the domain and range are each in one-dimensional space, all right? So that's another thing to kind of take away. In general, we'll see how that generalizes. So, all right. So I'll use this terminology, sometimes mapping. I kind of, I might go back and forth with the way I talk about things sometimes, but I might fall into this terminology of, saying that a function is a mapping from one space to another. So if I say that, that's what I'm talking about. So in this case, we're mapping basically one-dimensional space into one-dimensional space. That's what the high school functions do. They map the x-axis into the y-axis, basically, right? Now, another thing that we're going to do, we're gonna use this idea in the last bullet point. So if we identify points in the domain with corresponding points in the range, and what I mean by identify, I mean we almost think of them as the same point, right? Like we just say, okay, you don't have to, strictly speaking, think of them as the same point, but you just have this close identification of them, right? If you do that, then we can think of the function as changing the spatial relationships between points, okay? So let's see some examples of stuff like that to kind of bring that home. So we're going to do that. We're going to see that some examples of that, but we're going to do it in the context of activation functions. So let me give you a little spiel about activation functions. These are used in neural networks. We'll see what they're used for. We can talk about why they're used, how they work, and all that. But first, let's just understand them as like high school functions. Okay. So just here's kind of the library of common activation functions. All right. First one is called ReLU. It has a specific formula. It's the max of 0 and x. So it maps x to the maximum of 0 and x. So in other words, it maps anything negative to 0. And it maps anything positive to itself, right? So what is ReLU of the number 3 then?
1. I mean, 3.
3. It maps 3 to itself because 3 is positive, right? So what's ReLU of 0?
0.
It's 0. 0, yeah. So it will also map 0 to so it maps 0 to what? The max of 0 and 0, which is 0, right? So what's ReLU of like -5 then?
0.
0. Okay. So this is what the graph looks like. This is what the graph of ReLU looks like. Okay. So let's hit that point about spatial relationships using this widget. So what can I say? So with ReLU, any number that you can think of is a permissible input. Right? I can put any numbers. There's no restriction on that, right? So let me just pick two numbers, like these two numbers here. These two numbers on the x-axis, right? We got one red, we got one blue. How do they map, right? How is the x-axis mapped into the y-axis here? What can you say about the distance between this dot and this dot versus the distance between this dot and this dot? Can you say? It's the same, exactly. So there actually is no change in the spatial relationship between the dots as they exist here down in the domain, and then as they, they appear as they go through the function, right, in the range, right? So there is actually no spatial difference there. There is no change in the spatial relationship there. On the other hand, what if I choose two dots like way over here? What happened? Now I've got the spatial relationship between the two numbers in the domain. Well, is there a distance here? There's a distance between them, right? But what has ReLU done? It's basically collapsed those two dots together. So now they're the same in the range, right? So the spatial relationship between the two dots has changed. Make sense? Okay. Let's talk about some of the other activation functions, like, wait, that's not what I want to do. So I'm going to change this R to an L, and we see the logistic function. Okay? This is another.
Can you shrink a little bit, just so we see more of that function?
Shrink what?
Oh, I mean, like the graphs, you can see a little bit more.
Oh, maybe I can collapse this. What's that?
Yeah, just kind of see more of the shape of that function.
Yeah.
I have a question.
Yeah.
When you say the spatial relationship, is it okay to kind of think of it as like a visual three-dimensional thing, kind of, or do you just
Here, when I talk about the spatial relationship, in this context right here, I'm talking about one-dimensional space. So like 2 points on a line. So these two points on this line have a certain relationship to each other in one-dimensional space. Or we're just talking about the distance between them, really, right? So in one-dimensional space, that's pretty much what you can talk about. The distance between them, maybe which one is on the left, which one is on the right. That's also part of the spatial relationship, right? In one-dimensional space, pretty straightforward. So, let me ask. So, okay. First of all, are we visualizing the function okay, do you think? Or would you like to see it zoomed out?
I'll use it out a little bit more.
Okay.
Yeah.
The thing is, let me.
Yeah, and then keep in mind is like mathematicians will use the term like space in a way no other human being will use. So just kind of keep that in mind. That,
so just keep it abstract.
Yeah, it's very abstract. There are a lot of common terms that have a very specialized use. So just don't get too confused if there's like a sort of concept you're familiar with. Maybe use it in a much more specialized sense.
Right. No, but this is good because so I'm using the phrase spatial relationship, but like what I really mean, at least in this context, is the distance between the points and which one is on the left, which one's on the right. Right.
Or if you think of it like an angle, like if it's all on the x-axis, then there's no angle, right? I mean, the angle is zero.
So if you upgrade this to like two-dimensional space, then you can have the distance between the points, and then they can be rotated around like different in relation to each other in different kinds of ways. If you're in three-dimensional space, you have a whole other degree of freedom, and there's different relationships that 2 points can be in, right?
But we're staying in the first, right? Okay.
Yeah, but right now we're in one dimension, right? So let me ask you this. This is a question I had for you. So here we have these 2 points represented in the domain, and as they go, like they get mapped through the function, does the spatial relationship between them change? How would you characterize the change?
I mean, the distance shrunk between them.
Yeah, exactly. So it takes these 2 points, right, and it basically projects them onto the y-axis, and it decreases the distance between them, right? And generally speaking, if you look at this function, this is where Ahmed's right. We should zoom out. Try to zoom out a little bit. I wonder if I can unlock the
I mean, yeah, you probably just set your
I
x
think I
axis.
can unlock the viewport. There we go. So yeah, if we zoom out a bit, right, what we see is that the further you take these points out in one direction or the other, the more they're going to be sort of clumped together, right? Like if I take these points out further and further, right? Let me change the setting.
So you're basically kind of putting an emphasis on a specific range of value. Like some values that are closer to, I think, 1. I don't know what the intersect is there. Like 0.5.
Let me change the.
Sort of, yeah, because,
So I guess technically it's 0 and 1.
yeah, it's almost like, kind of like a Boolean function, always keeping a sort of continuous function, getting closer to that, almost a street like.
Okay,
Yeah.
I see it now.
So
You're basically like, the closer you are to 0, the more relevant the change becomes.
that's true. That's 100%. Like, so the closer you are, so this thing will like to sort of separate points out, right? So let me see if I can just adjust these settings properly. Why is this, my X is way up here, but it's not. Oh, I need to fix the slide.
Just it?
Yeah.
Just, you want to keep an eye on time.
Yeah. So if I take this way out here, right? And then I take this out, just a little bit. So what can you say about you see how this is much more pronounced now, right? Like the distance between these 2 points in 1D space is very large, but when you look at these points through the function, they're very close together, right? So the more, if points are more out here, they're going to be, as you look through the function, they're going to be closely packed together. And likewise, if you go in the other direction, right? But points that are down here versus points that are over there are going to be far apart. It's going to tend to separate these points out, except when you're in the middle, right? Does this kind of make sense? This is the nature of this logistic function. Right, so if I put these 2 points over there, like they would be now clumped. When you look through the function, they'd be clumped towards 0, right? Whereas if I put the 2 points way out here, they're going to be towards 1, right? So it's going to separate out points. So this is why this type of a function can be used in a classification setting, because you want the nature of classification is you're trying to pull things out. You're trying to separate them out, figure out which is which. Right?
Because it's essentially a discrete task where you're classifying, as opposed to like some kind of continuous task.
Yeah. It's like classify red or blue, right? Or whatever. All right. So beyond your high school functions of one variable, one input variable, one output variable, you have what you call multivariate functions. So functions that take more than one number for inputs, or and produce more than one number for outputs. Now, in this situation, the graph actually lives, okay, so if a function takes, say, n inputs and produces m outputs, right, then the graph actually lives in n plus m space, right? So as we just saw, right, in the high school setting, you had one-dimensional inputs and one-dimensional outputs. How much is 1 plus 1 again? 2. So the graph lives in two-dimensional space, right? So generally speaking, if you have n inputs and m outputs, then the graph lives in n plus m space, right? Now, of course, if n plus m is bigger than 3, that's when we stop being able to visualize anything, right? So in terms of the graph, we cannot visualize the whole graph, right? Because we can't visualize 4-dimensional space in height, right? So nevertheless, we can still talk about functions, right? You can design functions all day that take, a bunch of inputs and produce a bunch of outputs, right? That's not a problem. We can do that abstractly. You can do it with computers, you can do it in math. It's not a big deal, right? So here's just an example of where you can actually visualize. So this is an example where you can visualize the graph, but this is a multivariate function, right? So how many inputs are there? Two. And how many outputs are there? One output, right? So what's the formula for this function? F of x and y, right, is x squared plus y squared, right? So it takes two numbers in, right, x and y, and it produces one number as an output. It squares x, right, it takes x squared, and it takes y squared, and it adds them together, that's one number, right? X and y together produce one number, x squared plus y squared, right? So the graph of this is sort of this three-dimensional parabola, okay? So that's an example where you can visualize the graph. Where does the domain? The domain, of course, is how many dimensions? Two dimensions, right? Because two inputs. Two inputs means the domain is two dimensions. And what's the dimension of the output? What's the dimension of the range? Right, one, because there's one output, right? So therefore, 2 plus 1 is 3. The graph lives in three-dimensional space, right? Okay. So, of course, we can just, again, like I alluded to earlier, you can just start creating functions that, that just map, 4-dimensional space into 5-dimensional space, 3-dimensional space into 2-dimensional space. Like, so let's say this last one. So what's the space that it is mapped from? 4-dimensional space and mapped to 3-dimensional space, right? Because it creates this, it takes W and divides by 3, yx squared, and then z plus y, so it produces 3 numbers in the output, right? So the graph lives in 7-dimensional space, and we can't visualize that. On the other hand, I would like to point out that you could visualize, since these are 3-dimensional points, you could try to visualize just the range, right? Does that make sense? Likewise, like here, the domain is just taking the permissible endpoints, the permissible inputs are from a 2-dimensional space, right? So you could visualize that, right? You could visualize a point in 2-dimensional space. So I can visualize inputs on that top one. Let me scoot down so I can point at it, right? I could visualize this input because it's just the point in the xy plane. What's the dimension of the output? It's three numbers, right? So I could visualize this output as a point in 3-dimensional space. So I can visualize the inputs and the outputs, right? Although I can't visualize the full graph because for this function, the full graph lives in what? 5-dimensional space, right? So that idea that we'll be able to visualize inputs and outputs in isolation is what we'll use to visualize what's going on inside the neural network. Okay? Even if we can't visualize the full graph, we can visualize the points that are going in and the points that are coming out and see how the spatial relationships have changed. And that's how the neural network operates, by changing the spatial relationships between the inputs and outputs. Okay? So this is just a broad overview of what neural networks are. So we covered a lot of this, when Ahmed asked for what is it, TLDR? TLDR. What does that stand for?
Someone's not on Reddit.
Yeah, too long.
Someone said that on Reddit?
No, I'm saying like you don't have a Reddit. Most people think.
Oh, yes, exactly.
That's kind of phrase for someone.
I
Too
know.
long.
Okay, too long,
Didn't.
didn't read. Okay, got it. Okay, now. All right. Go shopping for some bell-bottom pants next. Okay, so, all right. So yes, type of machine learning model. Just an example of an application that has gets some media is like tumor classification. So a broad classification that you'd be concerned with for a tumor, is what? Benign or malignant, right? So a neural network might be trained so that you could give it some information about a tumor, like in the form of measurements, right? Like how long is it? How wide is it? Like what's its density? Those kind of things. you could feed it some data and get a classification out, right? So maybe so. The idea is yeah. Well, okay. Let me ask you this. So is it obvious now, like why we started talking about functions to begin with? Because that's what a neural network is, right? That's just what a neural network is. It's like you give it some input, it produces an output. You know, so it's just a mathematical function is all it is. All right. So we're just going to try to really from now on we're just going to try to understand the structure of that calculation and visualize. Okay. So yeah. So let's kind of out of these bullet points. We've covered most of it, but let's talk about sort of the structure of what a neural network is. I should have. I didn't. I should have gotten a graph to show you. Anyway, I'll just do one.
I gave you a graph.
I know. What happened to it? What did you do to it?
Yeah.
Oh, it was hard work.
You crumpled it up.
He crumbled over his shoulder.
I know. And now I'm begging. Now I'm back begging for it.
On your hands and knees. Oh,
It's too late. It's too late. though.
Woody Harrelson doesn't make.
All right.
I do have a baseball bat.
Look at the tab, the neural networks tab. Is that the one we want to originally put together, or?
I don't know. Is it? It's broken.
You broke it.
Right.
I broke the sheet.
You broke the sheet.
No.
I think, I don't know. Anyway, well, okay. I mean, you can Google an image of a neural network. So,
As long as you haven't said
here, let's.
Yeah, no, yeah. I mean, if you want to just plug into mine, I've got see the graphic throw away. It's right there.
Yeah, that one. I don't need that.
Okay.
I don't need that anymore.
See you.
Okay. I have Google.
Yeah. It is an adequate replacement.
I don't need real relationships. I have chatbots now. So, like, okay, if you just, Google neural network, so you get a picture of a graph, right? So it's what you might call a computational graph. So the graph goes a long way to kind of understanding like the structure of the calculation. Yeah.
Just may want to differentiate between the graph, like the graph of a function,
Sure.
and this kind of graph, which is just basically a network diagram. So
Yeah.
there are two different different things.
I should have said network.
Yeah, well, but they call them graphs normally, but it's basically a network diagram. So graphs used in two different senses.
Basically, like circles and lines.
Essentially, yeah.
It's what a network is, right? So a neural network is symbolized by this. So the idea is that it takes some input, right, and then that input is fed to each of these nodes, right, into the first layer of the network. So each of these stacks of nodes is referred to as a layer of the network. So we have our first layer, second layer, and third layer, and final layer, right?
The first layer is the input layer.
Yeah.
Yeah,
The
well,
ones in between,
yeah.
yeah.
Depending on how you want to label them. Yeah.
This would be a deep neural network because it has hidden layers.
Yeah.
So if every arrow is connected, they call it, they say it's a fully connected neural network.
Well, aren't they always fully connected?
They're not always.
Well, I got the discussion.
I guess it's something that says they have to be, right? Yeah. I'm sure. There are different flavors and varieties of neural
Right.
networks, right?
Sometimes, even if they're fully connected, sometimes they'll have a parameter that will ignore, just to avoid biases, they'll ignore one of the neurons, like.
Is this
There's also
why
the bias.
hallucinations exist?
No, it's a completely different reason.
Okay.
I mean, the hallucination may be a consequence of like overconnection, right? Maybe. I mean, I'm just kind of spitballing here.
It would be things like even almost like conspiracy theories.
The reason why it hallucinates is because it's not really trained to be right, because it's just trying to sound incorrect. So it will try to say whatever it sounds right. And because the only thing that the like generative AI models are doing is that you give a set of tokens, which are basically pseudo words,
It's like a very important.
and then you try to come up what is the most probable next step.
Right.
So just by doing that, it's just gonna come up with
Right.
what is the most probable sentence based on the previous sentence.
Right.
That's just gonna hallucinate.
So that's what the chat GPT is.
Yeah,
I've
that's-
never heard this called hallucination, but, okay, cool. I never heard that before, but, yeah, that's what chat GPT does, right?
But there are ways to prevent that.
I guess, I don't know. I mean, I'm sure they worked out a lot of ways,
Well, you can prompt it in a manner that.
Yeah, you can try to give it a better prompt.
Reduce
Yeah.
the probability of it happening.
Right, but it's still gonna happen.
It's like even real humans, you can hallucinate, right? Like you can say something you think you're right, and then somebody proves you wrong, right? So it's kind of like what's an hallucination?
It's when you see something that's not there,
Well,
or you hear something that's not there.
I kind of I give it that whole thing, it's, only paranoia if you're wrong. So it's kind of one of those things sometimes, I don't know.
Yeah.
Humans have it all the time, so I don't know if it's possible to completely.
What's this?
Like in general,
It's really fascinating stuff.
if you tell
That's what we're doing. Stuff like
the
that.
LLM things step by step
Yeah.
and verify, take your time, verify your response, you increase its accuracy
Yeah.
with just those.
It's depending on the tokens you use as input, it's gonna trigger different neural networks.
Okay. Well,
Sidetrack.
okay, so what I want to get a key takeaway. Well, the key takeaway, I think, looking at this picture is just kind of the general flow of the calculation that the neural network does, which is that the data goes in, it's processed by the first layer of neurons, the output of that is passed to the next layer, and then the output of that is passed to the next layer, and then finally you get an output which can be interpreted as a classification, okay, a benign or malignant, right? So,
Did you talk about the concept of weights in there or no?
not yet. So yeah, the idea, the key takeaway that a neural network is trained, which is trained to be a binary classifier, is just a function that assigns one of two labels to a data point. Right? It does that numerically in a numerical way, which then is encoded into the classification. Right? So the data point is fed into the function. It produces a number on the end, but that number is then interpreted as a classification. A common way that that's done is that the final output that the neural network generates is a number between 0 and 1. If, say, the output is bigger than 0.5 or some other threshold. But generally, if the output is bigger than 0.5, then you might classify the tumor as malignant. If it's not bigger than 0.5, then you classify it as benign. So in other words, the output is a number, and you have some way of translating that number into a classification. Okay?
I don't want to put benign tumor.
Key decisions that have to go into constructing a neural network are what? How many layers, right? How many layers? How deep is the neural network going to be, right? And then for each layer, how many little neurons? That's what the nodes are called. Those circles are called neurons. How many neurons are you going to put in each layer, right? And then what is the activation function? How is each neuron activated? And so that comes to that. We talked about a couple different examples of activation functions.
That's basically neural network architecture.
Yeah, sometimes that's referred to as. So this visualization, I won't talk much about it, but the idea is that the neural network is going to try to, in fact, I will talk a little bit about it. The neural network is going to try to construct a delineation between categories, right? So if you can imagine these points, that have two different colors. We've got the blue points and the orange points. The neural network will try to sort of draw a line, right, to that separates the points, the blue points from the orange points. All right. Now the thing is that not any set of points can be, and again, when I'm using blue and orange here, it's like as representations of some classification like benign and malignant, right? You see what I'm saying? Like, is it a dog or not a dog? So binary. Yeah, it's a binary classification, right? So the neural network will try to draw a line that separates one class from the other, right? Now, not all data is going to be so nicely laid out that you can draw a line between, to separate it, right? So this is where the change of spatial relationship business comes in. Okay, it's that you're going to try to take the points, even if they're not. There's a phrase in machine learning called linearly separable. Right, so these points here are linearly separable. So we've got two classifications, blue and orange, benign and malignant, whatever, right? And we can draw a line between them that separates them. So the formula for this line can act as a function that classifies these points as either blue or orange, right? You could cook up a function using the formula for this line. So, like I said, the neural network, however, is stronger than just a straight up linear, a straight up line. Because what the neural network can do is it can take those points and put those points through a series of spatial transformations to force them to be separable by a line. Okay.
So, now when you talk about separable by a line. Do you mean like a 2D line or a line through some n-dimensional space?
Yeah, so it could be. So good question. So a line in two-dimensional space, a line is a line, right? But of course, we could be talking about different dimensions of space. But ultimately, what was the output in this? At least in this scheme that we've been talking about, what's the output? It's a single number. It's a one-dimensional space. So actually, if we go back up here, in this setting, right? What are we doing? We're actually going to transform the data points now so they end up one-dimensional. So we're taking the data points. And we're doing all kinds of crazy stuff with them, and then we're going to put them all in a line. And we're going to have one number, right, that determines, which points are benign tumors and which points are malignant tumors. So in one-dimensional space, we're talking about a single dividing point, right? So
it's collapsing all those values down to basically like a one-dimensional.
Yeah.
Okay.
But if you go back, so that one point can be traced back into the original space to create, some curve or something that, it takes a circuitous route and classifies the points in the original space. But anyway, all right. So getting back to that. So a line in higher dimensional space, like in three-dimensional space, a line is a plane. And so on and so forth, so that's definitely coming. But, all right. So, moving on to, matrices. Moving on to matrices. So this is a matrix, right? It's just basically this sort of data structure, as it was called earlier, that has rows and columns, has a bunch of numbers in it, right? Sure, I have to.
You probably have to rerun.
I did it. Okay. So yeah, rows and columns. We talk about the dimensions of the matrix. That's just terminology in the context of matrices. It's the dimensions of that matrix are 3 by 5. It's just like hardware store stuff. 2 by 4. It's like 3 rows, 5 columns. It's nothing complicated. So that's a 3 by 5 matrix because it has 3 rows, 5 columns. Right? Okay. The numbers themselves are sometimes called entries. I might use that. So we identify a number by its indices, right? We do a double index to identify numbers, right? So the letter I here is the index for rows, and J is the index for columns. We might say, okay, what's the 2-3 position of this matrix up there? The 2-3 position is second row, third column, contains a what? contains an 8, right? So, you know, any sort of software development, computer science, you know what I'm talking about, right? I can identify the position of an array of a number in an array by the indexes, right?
So this would be just like normal human readable indexes, right? We're not talking, because like if you think about it programmatically, you would have thought it's actually the last row, fourth column. But like if it starts from zero,
Yeah, he's not in.
Oh, no, it doesn't start from 0, yeah. yeah, the indexing doesn't start at 0.
for me that was -6.
Yeah,
This is why Julia doesn't.
Yeah, okay, fair enough.
The only language in the world.
No, there are others.
I have to.
Well, other conversation we haven't talked.
All right, so that's the idea of a matrix, right? So how do you add and subtract matrices? Yeah, it's it's not a big mystery, right? So if I want to subtract these two matrices, first of all, to subtract or add matrices, they have to be the same dimensions, right? Otherwise, you can't do it. But how does this matrix come out of that subtraction? Just by subtracting the corresponding entries, right? So is it 2 minus 1 makes what? 3. There you go, right? 5 minus 2 makes 3. 3 minus 1 makes 2, and so on. So adding and subtracting is just straightforward, right? Just corresponding entries get added and produce the result that way. All right, so now doing multiplication is something a little bit different.
Just a final question
Right,
here.
so it might look like a lot at first, but just like anything, you can get used to it. So the first step towards understanding how to multiply two matrices is first understanding it doesn't work like add and subtract. Right? You don't just multiply the corresponding entries. All right. This is what you have to do. You have to just do this thing. It seems totally weird, but that's how we do it. So the second step to understanding how to multiply matrices is how to multiply a row by a column. And this is how you do it. So what do we do? With rows and columns, they both have rows and columns both have length to them, right? So I can say, what's the length of this row? 3. What's the length of this column? 3. They're not the same, it doesn't work, okay? Why? Because you have to match up the corresponding numbers, right? You have the first number in each case, right? 1 and -1, you have to multiply them together. Likewise, you have the second number. The second number here is 2, the second number here is 3, you multiply them, right? Here, the third number is -1, third number is 4, you multiply them. You do all those multiplications, you add them up, right? If you've taken physics, this looks like a dot product.
And just for everybody else, just use a package. I never bother remembering this. NumPy has packages that does this automatically. I'm the guy who says, hey, just use a package. We already have this problem solved. But continue.
So notice that the output is just a
NumPy.
single number. Okay, the output is just the number. If I multiply that what are the dimensions of this matrix? 1 by 3, and then this is a 3 by 1. So I do this 1 by 3 by 3 by 1. The output is just a single number. Okay, so that's how you multiply two matrices. And generally speaking, if I multiply a row matrix by a column matrix, it just looks like this, and you get this big ugly sigma sign out, right? That says you just this says multiply these two things, then you just add up the results, right? So that's it. So I mean, doesn't matter what the dimension of the matrices are, as long as they're the same length, right? The first one's a row, second one's a column. You just match up the entries. You multiply them, and then you add all that together. So that's how you do a row by a column. And again, the output is just a number. Okay. So we're going to stop for a second and say, okay, how does this? Before a short interlude here.
Pause for a moment. Any questions? Everybody good? Okay, so making sure.
Right. So you may recall this whole thing, right? You remember this y equals mx plus b thing from school? It's the equation for a line, right? Okay, so now what we're going to do is we're going to sort of generalize y equals mx plus b into this. But so the b is the same, right? So, okay, so let me pause for just a second. We're gonna take a point in n-dimensional space, right? And then we're gonna map it into one-dimensional space by this formula. We're gonna start by taking a bunch of different m's, not just one m anymore, but a bunch of different m's. How many m's? N. So we got m1, m2, m3, all the way up to mn. The n m's. So, but yeah, so we're gonna, these are called parameters or weights or like different things, but they're just numbers, okay, they're just numbers. And the x's here, now I have, how many variables do I have? I have n variables, right? So I'm gonna take the first variable and multiply it by m1. So I'm taking x1, multiply it by m1. x2 multiplied by m2, and so on and so forth, and add them all together. So that's what this represents. Then we have this b term from y equals mx plus b. So it's just a little extra number that's just spoken out there, right? So you got a b plus this sum of variables times a bunch of numbers. Then what we realize is that because this matrix multiplication, right, is just that, right? It's just that sum. So this is really this, x1 through xn maps into this matrix times this variable. It's like one big variable. It's a bunch of, I just call this like one big variable, right? And then these are just a bunch of numbers, right? And we get back to that form, mx plus b. Of course, I'm writing it as b plus mx, like if I were to give this a name. Okay, let me skip back to that, actually. So, if I call this m, like as I'm doing here, so if m is this row matrix with all these numbers, and then I call x this column matrix with all these variables, then by matrix multiplication, m times x is just that summation.
Also, just in terms of like lingo, what do we normally call these vectors, not matrices?
If you want.
Well, I normally
I mean,
because you're gonna see people use vectors for this. I think.
I wouldn't,
You wouldn't?
but
Why not?
I don't mind if you do.
Okay.
Yeah.
Just because normally you see like vectors used for basically one-dimensional matrix.
Yeah, but they're, I mean, yeah, that's fine.
The vector sounds cool.
I agree.
Yeah. See, yeah. So you're gonna
Would you be mad if you?
No, like,
Okay. So yeah. Okay.
totally fine with it.
We're talking about vector multiplication,
All right.
not matrix multiplication.
So we see that this is just mx plus b, right? So it's just high school stuff, right? It's just mx plus b, right? But where m is now what I'm calling a row matrix, right? And x is a column matrix that contains a bunch of variables, right? So that's it. So now what is a neuron? Now what is a neuron? So what we do is we let alpha be any activation function that we like, say ReLU or logistic or the hyperbolic tangent, which I didn't talk about, but you got all your choices, right? So all you do to construct a neuron is you take your mx plus b and you stick it inside of an activation function. Boom, now you have a neuron. That's it. That's all a neuron is. At least from a computational point of view.
And alpha is that fish-looking symbol, right?
Alpha is the symbol that looks like a fish.
Okay, just picture that.
Or a small
Greek. Huh?
Or a small.
It's like a cursive A.
Yeah.
So
Not also Greek.
Very small study fish.
I was using a capital A. I was using a capital A, but I didn't want it to look like I was just doing multiplying a matrix. But
You want a bigger function.
I wanted to give it a name. So alpha is the Greek letter A, right? So alpha for activation, right? Alpha for activation function. So it's basically, you've got b plus mx, it outputs what? Well, b here is a number. It's just a single number. M is this row matrix, right? X is a column matrix. So we do it row by column, we get a number, right? We add b. That's just another number, right? So we're mapping n-dimensional space into one-dimensional space, right? Okay.
So why is the B there by conception?
What? So I don't know. I mean,
I thought like more of a bias term.
Bias, yeah.
it's the bias term, but what is that?
So I like to think of it like when you look at the, like a linear function, without the bias, you don't have a way to go up and down.
Yes.
The functions, it's kind of like a similar concept, but obviously here's hard to visualize this. On a neural network, you might have a lot more dimensions, but
Yeah.
the idea is that it's gonna help with kind of certain biases that you can come up with.
Yeah. So you want to have that degree of, that extra degree of freedom. So if I go to do a little bit of a, go back to high school math, right? So without the B, you're limited a bit, right? When it comes to the lines that you can have, right?
So you just like slope of your line, if you want to like shift it up and down, it helps you with that, and it kind of gets you.
No, it's more like the order, like everything is of the origin, right? You don't have a B, it's like, it's at the origin.
So,
Yes.
so if, here's a line that's just y equals mx, right? If I let m vary, right, all I can have is these kind of lines that just, they all pass through the origin,
Yeah.
right?
Just your slope has changed.
But if I have mx plus b, right, then I get a lot.
Do you want to fix your m just so to make it easier to see?
Sure.
Like see like what's.
Like that little fancy line.
So you get a lot more variety. You get a lot more lines that, and that's what you want with the neural network. You want to have it enough degrees of freedom to work with so it can reshape things the way it needs to.
Moves the line itself, like translates it.
Right. So if I don't have a B, right? If B is just 0, just delete it, right? Then all I can have is these lines that go through the 0, 0 point, right? So it can't sort of range, it's not the full family of lines, right?
Was there a question? Did you have a question?
No.
Oh, sorry.
I'm concentrating, sorry.
Oh, no, that's fine. I just want to make sure we didn't like skip you over the question.
And kind of a two-part question, like programmatically speaking. So this might be more of a question for you. But is regular sort of like the standard activation function that's used most of the time? And then I guess the second part is what determines what kind of activation function you're going to use?
Yeah, that I'm not sure I can tell you. I can tell you that a lot of times you just try a bunch of stuff to see what happens. Yeah.
Rate is common. I don't know if it's the most common.
It is the most common.
Yeah. And by the way, I embedded a link to Wikipedia about activation functions if you look through the sheet. And of course, you can just Google activation function in Wikipedia and it'll pop right up. And so you can see the whole library of activation functions, right? So the logistic function is also very common. It's also called the sigmoid function. It's that one that looks like this, right?
It flex and then down. It's like my favorite function.
Yeah,
Literally,
it's kind of like
it's cool. It versus all of them. And that's a very, very common application.
All right, so now everything is downhill. Matrix multiplication, like the full version of matrix multiplication is just row by column again and again and again and again. Okay, so how if I want to multiply these two matrices, right? And first of all, I have to notice their dimensions. This is a 3 by 2, and this is a 2 by 2, and the output of that has to be 3 by 2. We'll go into all that details. But this is the calculation. If you look at the calculation close enough, you see why the dimensions have to be 3 by 2 for the output. But basically, to get this, let's just understand one of these, and then you see what's going on. So this -1, 1 plus 7 times 5 comes from this row by this column. So once you understand row by column multiplication, you can do any two matrices, right? So the point is that we have this, operation, okay? And this operation is going to form the basis of another structure, a bigger structure in the neural network, right? So there's this question of can you multiply two matrices? Question of are the dimensions compatible, and so on. And, you know, if they're not compatible, then it's an undefined operation.
Or just undefined.
Right. Undefined will tell you if they're not compatible.
Yeah, we got packages, I'm the package guy.
It's gonna-
Use package.
It's gonna complain.
Yeah, it'll tell you like, yeah, the rank is incompatible.
So here we get to linear functions again. So it's like the Dragon Ball Z final form of linear functions, right? Again, the final form is just mx plus b, right? But now m is like a full-blown matrix, right? X is still, it's a column of variables, right? And b is a column of numbers, fixed numbers, okay? So again, we have these two major parameters, m and b, but they're matrices now, right? But it's still y equals mx plus b. And this is what it looks like when you do the final computations. Now, it's worth noting that each of these individually are exactly the form that came out when we talked about neurons. So this is just a column of neurons. What do we call a column of neurons? A layer of the network. Remember? So the network has layers, right? You pass the data into the first hidden layer, and it produces an output. That output is then passed to the next layer, and so on, right?
Real quick, sorry.
Yes.
So you talk about the column of neurons, a little more specifically, that would be like the column of the connections between them. It's actually what the synapses, right? Because that's where the weights are.
Right. So this is without the activation function. Right. So yeah. So then So to really get the layer of the neural network, you need to apply the activation functions to each one of these. Right. So you apply your favorite activation function like ReLU, sigmoid, hyperbolic, whatever, and then you've got the layer of neurons.
So is a column without an activation function essentially useless?
Those are not shown to be very effective in practice.
The activation function is what makes it.
Yeah. The activation is very helpful.
Would the lack of an activation function be a type of activation function?
Yeah.
So
Identity function, right?
Yeah.
Activation function.
Yeah, even in sklearn, I think that's even an option.
Yeah.
So you could choose ReLU or logistic, or you could choose identity. I think if you choose identity, then it means that there's no activation function. Right?
no activation.
So what is a layer of neurons?
That contains itself.
A layer of neurons is y equals mx plus b with an activation. Okay? So that's it. So for each layer of the neural network, what you have is a matrix, and a matrix that obviously can be stored, and then this vector, you like that?
Yes.
Okay. Then this vector of, what we call bias terms, or the y-intercepts from high school, right? Okay. So, and then you wrap that in the activation, and the activation here is applied to each because now the output of mx plus b is actually a vector like that. It's a bunch of numbers, right? So you apply the activation, because the activation can only take a number for an input, right, and produces a number output, right? But here, so you just have to apply the activation to each of the entries individually, right? So it produces then a vector of numbers, or a column matrix. A vector is a column matrix.
Well, it could be. You can also have row vectors.
You can also have row matrices.
Row vector. Hey, okay. We'll talk after.
But we can all agree it can't be diagonal. That's all.
It can't be diagonal.
Verbal or something.
There's no diagonal matrices or vectors.
That's good.
Oh my goodness, this is nerd talk.
Okay.
Okay.
Well, you have the
So-
transformations of some of the diagonals.
Now here's
Identity matrix. That's one of the ones.
so here we go, y'all.
Okay, I'm sorry.
So I've set up a bunch of data to run through a neural network. So we have a trained neural network already. Okay. Well, no, we're going to train it right now, but it's just going to take a second. So here's the linear data that the linearly separable data, right? We got two classifications there. You got your malignant tumors over here, you got your benign tumors over here, all right? So let's run this, and we're gonna visualize each step of what the neural network is doing, right? So this is what's going into the neural network, these data points, right? Okay, what's this thing gonna do? Finches.
Yes.
Okay, back it up. Okay, so this is what it did. So here's the input. So this is what the first layer did to it. Okay? First layer, I should have told you the configuration. For the configuration of the network is that the first layer has 3 neurons, and so the output is in 3-dimensional space. Okay? So this is, all those points were transformed into this point cloud here. All right. So again, this data is very nice data. It's already linearly separable, right? Like it's already, I could write an easy classifier for this thing. I don't have to do a neural network on this thing, right? It was already a line I could draw right through the data, and it'll classify red or blue, right? But this is what the neural network did to it. So it did this, and then after that, it's basically, it kind of realizes, oh, you know, this is really just one-dimensional data if you just squash all the points together, right? And so that's what it did. Squashed all the points together. Now then they're still clearly separable, right? I can draw a separation barrier right there. Now I can separate red and blue, right? And then finally it says, oh, let's smash this down to 2 dimensions. We're already there anyway, like really one dimensional. And then finally, this is the result. The activation on the final step is the logistic function. So you remember that that's going to pull the points even further apart. Right, so that's what you see in the final step. Question?
So this looks very similar to what we saw last one. I think.
PCA? The PCA?
Yeah, when you're basically just squishing like multiple dimensions into a lower dimension.
Yeah.
True.
Like the PCA.
True. Yeah. That's why I think PCA kind of acts that way. Like it kind of does the clustering. It's in some cases. That's why, because it does a smushing thing. It doesn't always work, right? Because that's not what it's designed to do, but in some cases it does it because the data is just that way. Like it has that separability inherent in it, so it just like when it squishes it, it just makes it separated.
Yeah,
and squished, which makes it easy to visualize.
Yeah, because we took that 3-dimensional heart attack data and squished it, and not only was it linear separable, but where it wasn't, the neural network also struggled with it. Yeah. So it does very much look like what the PCA is doing. Good catch.
Yeah, that's a good observation.
PCA is fun.
Having a hard time.
Let's roll down.
I can't.
What is your surface failing?
It is. It is.
Yes, I know it is.
It is. Okay. Oh, it worked. Okay. So. All right.
You need a GPU.
Hold on. I need to do this here.
Is there a GPU?
Right? It's not. It's actually a surface. It's not actually a bad system. But I have to give you something.
I'm having this thing is not scrolling the way I want it to. Anyway, so let's go back to the let's switch out the data set. So that one is pretty straightforward to look at, right? I think it's just like it's like I'm getting a lag.
Do you need to use by system?
Maybe it's the Wi-Fi.
It's not a surface, it's a humble HP.
So let's look at the parabolic data. Okay. So the linearly separable data is an easy task. That was a cakewalk, right, for the neural networks. So let's look at the parabolic. So this is, when you look at this data set, right, what do you notice? Number one, you can't draw a line through the reds and the blues and separate them out, right? So that we have to somehow change the spatial relationships between them, right? We got to straighten this thing. Okay, so What is the network?
So just really quickly, can we go back to the original graph?
Yeah.
So yeah, so just click also so you see, so you use the term linearly separable, right? So you can separate it with a curve, right? But you can't separate it with a line. Hence the linearly separable.
Right. So I used the parabola to generate this data, right? So that's why you see this sort of parabolic shape through here, right? So it's not as easy a task for the neural network, right? Because it has to figure out, how that parabola basically. So what does it do? It sort of like smashes it down like this, right? And now it's starting to look a little bit better, right? Like I could maybe draw a line through it, right? So let's go through, see what it does. Then it kind of says, okay, it actually comes up one dimension. It's still in 3 dimensions actually. So it would come up, yeah, because it's still 3-dimensional here. Right, so it kind of rotates the points out. And you see it kind of like stretches them out a bit, right? So it's working on like configuring them so that you can draw a line through them, right? So finally we get this thing. And
Yeah, I take care of my system. Okay, so. Okay. So you want to
hope it doesn't fail.
Yeah, now you said, okay, which one do you want to see?
So yeah, we're right there. So it's kind of that right there is where it was like stretching it out, right?
Mm-hmm.
And then the next picture, it basically collapses it down to 2 dimensions, right? And now you start to see like it's totally separable. Then the next one.
Yeah, well, almost totally, right? You get a little bit of misclassification here, but for the most part,
Yeah.
you can go through all of it, right?
And then finally it smushes it down to a line, right? And now you can if you try to separate right here, you're gonna have like 1, maybe 2 misclassifications over there, right? So.
But you're generally gonna have some classification errors, so that's not unheard of.
And this is your upgraded, 3D plot.
The point cloud.
Where you can actually see this is the first layer, I guess. So you can see how it's, it works pretty hard even on the first layer to separate out, collecting all the reds over there and all the blues elsewhere.
So you kind of see from different angles of the plane,
Yeah. So that it really, okay, I'll save that point for the last one. So go ahead, let's see the last data set. So go up.
This is all you have.
No, go up. You have to live code it. Sorry.
Okay. So.
Go up here. Put it here. Instead of parabolic, put in annular. ANNULAR.
Para-annular data?
No para.
Okay. This guy, right? Annular?
1A.
Oh, that's how you spell annular. Okay.
Yeah. So it's basically you have like concentric circles of data points. So now you definitely can't draw a line through that, right? It has to figure out what to do with this. All right. So let's see what it does. First step, again, what it does, it upgrades from 2-dimensional space to 3-dimensional space, and it just smashes down the center this way, right? That's a totally reasonable thing to do, right?
It basically like your 0, 0.
Yeah, it's like smashing it down towards the 0, 0, 0, right? So so that's the strength of introducing higher dimensions, right? Because if you introduce higher dimensions, you get a lot more degrees of freedom to work with to try to separate out these data points, right?
It doesn't work up here.
What do you mean? I can definitely draw a circle. I need to go to 3D space.
No, for sure. But and in fact, that's what the neural network is doing, right?
Yeah.
Like it's just it's translating it into a space that is separable by a line. But then, if you translate that backwards, what you'll get is a circle right here. So we can't really go into all of that, but it's both. It's doing both. So it's first making it linearly separable. But then you can translate that back into whatever the boundary is supposed to be, right? So it's trying to again. The core concept is that you're rearranging the spatial relationships of the points, right? So you introducing a third dimension gives you that degree of freedom to push those red points out this way and to separate them from the blue points. And then from then on, it's sort of downhill, right? So now you get, they're really totally separated out here, right? And at this point, you just sort of it just starts reducing dimension until you get down to one dimension, and they're just totally separated out.
And of course, your point cloud, which is very similar to our last point cloud.
Right. So this is if you want to see it kind of from different. So again, that's the output of the first hidden layer. Taking those two-dimensional points and mapping them into 3 dimensions in this way starts the separation process. And really, that's the hardest part, right? And after that, it's just kind of downhill. After that, you're just like smushing the points down into lower dimensions until you see they're just totally separable. That's it. So, what do you think?
Pretty cool.
Yeah.
Definitely cool.
So I
That
guess
was cool first time I saw it.
So I guess like if you put more than 2 dimensions, it wouldn't really make it worse, right? It would become maybe like diminishing returns, but I don't think it would make it worse, right? Or do you think there's
So
a
putting
point-
more than 2 dimensions
Like
where?
what I'm trying to say is like, do you think like at some point adding more dimensions would actually make it perform worse? Or do you think it's
Yeah, I mean, it could, yeah.
Yeah.
So.
It's weird, but sometimes, yeah.
I think it might make it harder to search, right? Like theoretically, like adding more degrees of freedom shouldn't hurt anything, right? Because you're just adding more freedom, right? So like there'll be more ways to separate out the points with more dimensions, right? But I think it might make the search space more difficult to search, just because you're broadening the search space, because you have to train the thing.
Yeah, so you
Right.
need more data.
Exactly.
Yeah, that could be one way.
So if you keep the number of rows constant and you increase the number of dimensions, chances are you're going to actually damage your ability to predict, because now you can't sample as much unique data. So you kind of, if you think of it in terms of like ratio, and we talk about actually the machine learning class, right? We took machine learning class together here. And if you look at it as a ratio of the number of columns to the number of rows, as you increase your column, keep your rows fixed, there's less ways you can it becomes more fragmented, and you get less of a good sample of data. Now, of course, if you increase both, it's kind of up in the air. But if you increase one, not the other enough, then yeah. Does that make sense?
Yeah. So, also, isn't there the danger of overfitting when you have a lot of dimensions?
I mean, assuming you can even find the patterns, because again, there are a lot of dimensions with unique data and not as many rows. The overfitting one, I mean, if you do cross-validation, you should be okay.
So like usually overfitting, the problem comes when you train it too much and
Right.
then it learns to copy rather than get analysis.
Yeah, if you hold back like 20%, as your test data, and say train at 80% of the data, you should be okay, right? So the cross-validation should help protect you from overfitting.
Yeah.
Yeah.
I mean,
Yeah.
for sure. I mean, that's the point of it. But I just seem to think that like more dimensions means more parameters, which means you can have a more complicated model. If you know what, and overfitting is essentially an overly complicated model. So that's kind of why I make that association.
Also,
But anyway,
I'm sorry.
Can you
I'm not next.
put up the tumor slide one more time? The graph.
Oh, you want to see tumors? Okay.
Yeah, that was a very basic and it made sense there.
Okay. Let's see. The tumors. Do you remember where your tumors were?
It was like
I just remember the
Oh, the
design.
decimals switch. Okay.
Yeah.
It's okay. We can't
The
find it.
next after that. After that. I think it's in the bit about neural networks. Oh, sorry. Yeah, it was way after that.
Okay, it's a little
Keep going
further.
down. Yeah, it is.
Okay.
Yeah,
So,
I mean, this isn't necessarily the tumor stuff, but yeah, that's how I was explaining it. Like these are benign tumors. These are malignant tumors, right?
Yeah, can you go down just a little bit to the active, because there was a thing that said 0.5 or point.
Oh, the ReLU?
That part. That was just looking for that.
Oh, that was ReLU is what you're looking for,
I think
right?
that was above an activation of functions.
Sorry
If you
about
go
that.
to the table of contents under activation functions.
Yeah, I think so. Isn't it ReLU?
Yeah.
Oh, yeah, I could actually look for the table of contents, but okay, you got ReLU.
Here's that. Well, that's just the code.
Right.
Like
Like here, right? Is that the one?
Yeah.
Max OX, or looking for something else?
And then he said something about the tumor being 0.5.
Oh, the output being less than or equal to 0.5?
Yeah.
Right.
I'm sorry, that's just what I remember, and that's where my brain.
Whoa.
Yeah, where did you have the, where did you have the?
Well, that, I mean, yeah,
You designated something else, but that's what you chose, right? Like 5.
yeah, that's a common cutoff, because what you're doing is you're interpreting those as,
Yes, thank you.
if you interpret them as probabilities, right, then you say it's more than a 50% chance that it's this classification, or less than a 50% chance that it's that classification.
It's like microscopic.
It's not like a confidence
you
score.
would
Yeah,
do
yeah,
biopsy.
yeah, it can be interpreted.
Right,
like that.
exactly, like whether you wanna err on the side of caution or basically, yeah.
But I know there's like this, there's also like different like ways of make outputs. Like you could have either like you were doing where it's just like one output neuron,
Yeah.
and then you have like 50% up, 50% down. But you could also have two, and then you could have one neuron represents the confidence that is benign, and the other one means the confidence that is
Yeah.
malign.
Yeah.
Yeah.
No, I just like this
So
one.
you could take that numerical output and then also use that,
Oh, yeah,
that
so-
analysis. You could, like 51% is not very confident, but if you had to choose one, you would say it's,
No, I just like this example because obviously a tumor is a very complicated situation, but to boil it down to pass or fail
yeah,
makes sense of you massaging the data so that you can draw that line with the activation function. So that's why I really like that part, because it's simple enough, but then it makes, with the benign thing, it makes it more advanced thinking of like, okay, so this works on
yeah.
really complex things,
Yes,
not
yes,
just,
exactly.
gotcha.
So, and also generally speaking, you have much higher dimensional space you'd be working with, right? Like a tumor has many attributes, right? Has, it has dimensions, it has density, I don't know, but.
You could also have like usually what you,
I don't know,
what you would usually see as well is like, let's say you have an image, then your dimension would be every pixel of that image. Then you
Yeah.
can use that, let's say it's like a MRI or whatever, and you can use that where every pixel is an input, and the output would just be, is this a tumor or is not?
Right. So I just liked it because it makes me think that there's a lot more under the hood than just that line, right? So
Yeah.
Cool. Yeah, it's a good lesson. Thank you.
Yeah, and as Bryce was also saying, you can also have it to where your output neurons actually give you like a sort of confidence estimate, right? Where instead of one output neuron of say 0.5, benign and not, you have an output neuron for benign and for malignant, and the number will give you like a confidence that it's this or that, right?
You see that on like object classification.
Yeah.
Yeah.
The confidence score or whatever. Yeah.
Yeah. And now you know how well you trust your results, and even if you got a little bit of.
Hey, back onto where you guys were going on the hallucinations and stuff. Have you messed with the temperature settings on ChatGPT?
Yes.
Yeah, it's kind of interesting. So the way somebody explained it was like, the temperature is like, say you want ChatGPT to talk about pizza, right? It'll say like, so it'll say pizza, I love pizza, cheesy pizza with pepperoni pizza, blah blah blah. And then you can like go the opposite, and it'll say the Italian authentic dish with pasta sauce, and never say the word pizza, but describe the same.
So you can think of it this way. So the generative model, what it's doing is it has the input will be your words in a way, and your output is an extra word. Like based on these 5 words, what is the next word? And then what it gets is kind of like a probability, like this is like 99% probability that this will be the next word, and 98%, and then it kind of chooses those, and then your temperature will make it the higher temperature, make it so that it chooses words that are less
likely one, right.
So it makes kind of like randomness.
Computational power.
Well, it's not exactly randomness, because you're still describing the same thing. You're just detracting you're coming from the opposite direction.
Well, but it's like if you bring it.
So it'll be random around the same data?
Well, I guess it's not really random. Like you would technically.
Yeah, I guess.
Well, like filtering.
It's like, of course, when it comes down to implementation.
In a way, like I guess that's
It's almost like how obvious, predictable.
Yeah.
Temperature is a way of reducing the political correctness, right?
It can be, right.
Like you want it to give you real answers rather than some sanitized,
But they're
feel
all
goods.
right?
What the
Theory, you can get ideas for.
probably accepted answer almost like.
Well, right.
I don't think it's.
But you can prompt it too, you don't even have to rate the temperature. You can use a temperature, or you can just prompt it.
No, I use the temperature not for that kind of thing,
we
but
have
more
even beyond
as,
like just
uh,
n-dimensional.
say you write some code, it can write basically an inverse function of that code.
Dimensions of space.
By, see, and so it's very interesting.
Like, what I,
But again, same thing.
Oh, yeah, if you do the.
If you tell it to act on X,
Literally, like you
There
can
it
one
does
dimension,
the same
two
thing.
dimensions,
Zero, two,
So you can use that on a blockchain.
More
Beyond,
variability
and
in the
then
response.
beyond
To
that,
improve
you can have different
change.
Or get it on the right decision tree.
so like,
Yeah.
there's,
But if you say act on an X, it's going to
dimensions
give
and
you
represent
different
types of
types of
infinity.
results. of that.
So,
Yeah, the weird connection I also made was, in quantum physics, a very small probabilistic chance of the particle being somewhere. Feynman came up with the idea that it's in that place,
it's hard.
just
but it's
only a little bit of it is in the place at the exact same time. Most of the probability of the particle is over there.
It comes down.
And
to
so
this.
similarly with these
In three-dimensional
probabilistic
space,
models,
you can describe any
it's
point.
the next word after I is probably and or something, right? Like that's the 80% one.
Yeah.
But quantum physics would be a very 0.0001% token chance, right? But it's still weighing it just like in quantum physics.
yeah, I
It's
mean,
very weird.
I've kind of thought like, when you, let's say you take a model and when you train a model like this, it's in a way, it's kind of like a compressing algorithm, where you take a lot of data, text data, and you compress it into these neurons. And then based on what you're telling it, it's gonna give you outputs.
The reason I brought this up.
It kind of behaves a lot like